Okie dokie, today we're going to talk about Unit 3, Lesson 2, Continuity and Piecewise Defined Functions. I'm doing piecewise defined functions right now in my Algebra 2 class, and we did do those in Algebra 2. As many of you stated, it was kind of a foggy topic, and we're going to talk about it again in this class, and then we will use piecewise defined functions a lot in calculus. Piecewise defined functions were created so we're going to start this lesson out talking about the continuity, the pre-calculus definition. The graph of a function is said to be continuous if one can sketch the graph of a function without lifting one's pencil. That's what it means to be continuous. A graph that is continuous has no gaps nor holes. The graphs of linear functions and quadratic functions, which we have studied thus far, are continuous over the entire x-axis. Linear or quadratic models that are discrete models are not continuous. We don't have to worry about that. We haven't talked about or looked at many discrete models. Linear functions, quadratic functions are continuous because I can sketch them without lifting my pencil. Discontinuity, the pre-calculus definition. What does it mean to be discontinuous? It means the pre-calculus definition. The graph of a function is said to be discontinuous if one must lift their pencil when sketching the graph. A discontinuous graph will have gaps or holes. The graphs of discrete functions are discontinuous. The true definition will be discussed in calculus. So here's our first example of a discontinuous function. This particular function here is discontinuous, if I look at this first function a, because I simply, when I'm graphing that function, I'm going to graph it in yellow. And then what must I do? I have to lift my pencil to sketch that graph. So that graph is not continuous. That's a discontinuous graph. And it's discontinuous at whatever this x value is right there. We don't know what that x value is because it's an arbitrary graph. Here's another example of a discontinuous function here. Sketching the function. And then notice that there's this hole in the graph. So I have to pick my pencil way up, come back down, and continue the graph. This has discontinuous, again, at this whatever a value this is here, because there's a hole in the graph. Both of these, this is what we call infinite discontinuity, and we can write that in our notes. This is infinite discontinuity. And this is just discontinuity. You know, if we want to, we can call this whole discontinuity if we want. It doesn't really have a name until we get to calculus. Okay? So there's your two definitions of... Can I put this over here? I'd rather it be over there. Oh well. Daggone it. It's all right. Okay, piecewise defined functions. A piecewise defined function is a function that is defined by more than one equation. We began our discussion as stated before in Algebra 2. Each of these different equations are defined over different intervals of x. That's going to help us to realize that they're defined over different intervals of x. Piecewise defined functions, as stated before, are vital in the study of continuity and differentiability in calculus. They are simply pieces of different functions, hence the word piecewise defined. Here's a simple example of a piecewise defined function, and I'm not quite sure if we're going to graph this I think we do graph it on the next page. But so this particular function is a quadratic. The top of it is quadratic. The bottom of it is a linear. And it's defined, so it's quadratic if x is less than or equal to 2. So if x is less than or equal to 2, I'm going to use this quadratic. If x is greater than 2, I'm going to use this linear. So let's find the following function values first and foremost. If I want to find f of negative 3, I need to figure out where negative 3 is. Well, is negative 3 less than 2 or greater than 2? Negative 3 is less than 2. So f of negative 3 is simply going to be negative 3 squared plus 1. I really don't. Maybe I can fit it in there, which is 10. So f of negative 3 is 10. So we can put these points over here. So this is negative 3, 10. That's a point on the function. F of negative 1. And then I have to figure out where in the world is negative 1 at. Well, negative 1 is less than 2 as well. So I'm going to use the top piece to evaluate f of negative 1. And f of negative 1 is going to be negative 1 squared plus 1. And that's going to be 2. And that's going to give us the point negative 1 comma 2. F of 0, again, I need to figure out where in the world 0 is. 0 is here less than 2. So f of 0, I'm going to use this equation, is simply 1. And that's going to give us another point, 0 comma 1. This is actually the y-intercept of this function. And, where is 2 at? 2, it's right here. 2 is less than or equal to 2. So I'm going to use the top piece to evaluate f of 2. And this is going to be 2 squared plus 1, which is equal to 5. So that's going to give me another point, 2 comma 5. I'm going to find 3 more function values for this particular function. Now I want an f of 4. Where is 4 at? 4 is over here greater than 2. So I'm going to put 4 into this guy right here. So f of 4 is going to be 1/2 times 4 minus 2. 1/2 times 4 is 2. Minus 2 is 0. So that gives me another point on the graph. Let's label that point over here 4 comma 0. That's going to be an x-intercept of this particular graph because it has a y-coordinate of 0. F of 6, where in the world is 6 at? Well, 6 is up here in this piece right here. So I'm going to use that piece to find f of 6, and that's going to be 1/2 times 6 minus 2. 1/2 times 6 is 3, minus 2 is 1. So that's going to give us the point 6 comma 1. Okay. And f of 12, I realize that 12 is up here again. So f of 12 is going to be 1/2 times 12 minus 2. This is going to be 6 minus 2 is going to be 4. So here's our point 12 comma 4. Okay. So I believe in the second part of this, we're going to graph that, so now we're going to actually graph this particular function. Okay. And I'm going to graph this function just like we learned in Algebra 2. Do you remember how we learned to graph piecewise functions in Algebra 2? For those of you that had Miss G, she may or may not have done this. I'm quite certain that she did it correctly. But there is a tool that I used when I teach graphing piecewise functions that helps. That's just an aid in graphing those. Can anyone? So step 1 in graphing piecewise functions, we're gonna determine where the domain is divided, and we're going to see it's divided at -2. So we're going to sketch a light dotted line at x equals -2, and I'm going to go do, 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 do. You're not even going to see it because it's yellow. Make sure it's dotted, make sure it's yellow. All right, and we're going to see that when x is less than or equal to 2, I'm looking at this easy quadratic 2 graph. This is a quadratic that opens up because A, the leading coefficient of x squared is positive. It's going to open up. And in fact, the minimum is at 0, 1. So this graph looks like this. And what I'm going to do is I'm going to put a solid circle here because it's equal to 2. And I could go back to the previous page and look at these points. Oh, -310, -110, 0, 1, 2, 5. All of those points are on this particular graph. And we can label, well, this guy here is going to be 2, 5. And that's going to be an important part. And then you can label these other points that we found. Now we're going to graph this line. If I were going to graph that line as an entity, as a separate creature, not as a piecewise, what would I do? I would start at -2 and do what the slope says. Go up 1 over 2, up 1 over 2, up 1 over 2. Well, I can't start at the x on the y-axis because it's only defined, this line is only defined over here. So I'm a little bit, golly gee, if I did that line, I can do this easily with my Surface Pro, because look what I'm going to do. I'm going to graph at -2. I'm going to go up 1 over 2. And what am I going to do? I'm just going to do this. And erase that part of the line. That might not be accurate. I need to find some points. Okay, so golly gee, I've already found points. And what's some points that I found? What are some points that I found on that portion? Going in the wrong direction, dude. I found 6, 1. I had found 4, 0, 6, 1. Let's just plot those 2 points. This guy here is, was that 4, 0? It was, correct? And then if I go up 1 over 1, that's going to point is going to be 6, 1. So those are those 2 points I found. I could have done that too. I could have just plotted those points and then sketched that line. And here's my question to you. And here's what we need to be able to do. I'm going to put an open circle on this x equals 2 line. It's open circle because that line is not defined at 2. It's when x is greater than 2. And that's one of the areas that the Algebra 2 students yesterday were struggling with. How do I know to put the open circle or closed circle? You put the open circle when the x value does not equal that value. But you have to sketch the line all the way to this line, x equals 2. And in theory, this vertical line is not part of the graph. The part of the graph of this piecewise function is simply the blue and the purple. And another thing, if it is a piecewise function, you will never have a solid circle over a solid circle. It has to be a solid circle over an open or an open over a solid. Okay, otherwise it wouldn't pass the vertical line test and it wouldn't be a function. So now, here is a question. Is this graph continuous? Okay, Ethan, why not? And that's the reason that we're going to give in this class called pre-calculus. This is not continuous because I have to lift my pencil. That's the actual written verbal reason I'm going to write here. This thing is not continuous since I must lift my pencil to sketch the graph. Okie dokie. Example number 2. Graph the following and determine any x values where the function may be discontinuous. Step number 1. If I'm going to sketch that, step number 1, what will I do? Lily, do you know that? What's this first step in sketching this piecewise function? Yes, I'm going to sketch these lines, x equals -3 and x equals 3. So here you go. I'm going to label them down here. I'll label them in green. X equals -3. X equals 3. Oh. Sometimes the easiest pieces are the hardest to do. This top piece, what is this top piece? When x is less than -3, what is that top piece? It's just 5. The output is always 5. The function value is always 5. So I'm going to come over here and I'm going to sketch a line at y equals 5. It's kind of freaky, but it is y equals 5. And I ask myself, is that an open or a closed circle? Open because it's less than 3. And now if I am between -3 and 3, what kind of graph do I have? What is the middle piece? The middle piece is what? So now I know between -3 and 3, it's a quadratic. It has a vertex of 1, -3. And I know it opens up because a is equal to 1/2, which is positive. And now I want to find out exactly where this quadratic that opens up, that has a vertex of 1, -3, hits this line x equals -3. So I'm going to evaluate this function at -3. And I notice that -3 is in the middle piece. So I'm going to put -3 in the middle piece. And here I go. -3 minus 1 is -4. Square root of 16. 1/2 times 16 is 8. 8 minus 3 is 5. Oh, that's interesting. So now I know this point -3, 5 is on the graph. So look what my quadratic is going to do. It's going to come all the way up here and go, oh. And it's going to be, oh, guess what I just did? I just filled in that open circle. Because that point right here, -3, 5, is on the graph. The other thing I have to figure out is where, if this was equal to 3, where would it hit this other vertical line, x equals 3? This is a part that is difficult for students to wrap their head around. So what I'm going to do is I'm going to So I really need to figure out where this green graph, is going to hit this x equals 3. But if I try to do this, I'm going to tell you, if I go f of 3, 3 is in this piece, I have to use this bottom piece there. So if I evaluate f of 3, I have to use the bottom piece because that's where the x is equal to 3. X is greater than or equal to 3. So I'm going to put 3 into that, and look what happens. 3, well, let's go ahead and write it out, Lee. This is going to be 1/3, 3 minus 3, which is 0, hello, neighbor, plus 1. So that's going to be just 1. So this point 3 is going to be 1, and it's going to be a closed circle, and it has and then this is a line. This is a line in point slope form. That already I knew that 3, 1 was on that because that's the point 3, 1. The slope goes up 1/3. So that graph looks like that, and it's going to be a closed circle, but dad burn it anyway. I still don't know what's going to happen here. Here's what I'm going to do. Give me a value less than 3. This is kind of hard for students to wrap their head around. If I want to figure out where that graph hits this x equals 3, I can't do f of 3 because f of 3 is in this piece. What I'm going to do is I'm going to do f of 2.999999999. Because where is 2.99999? Well, 2.99 is right there. So I'm going to put this in, and what part would I use? I would use the middle part, correct? Because 2.999999999 is less than 3, so I'm going to use the middle part. But I'm not going to put that number in there. I'm just going to put, I'm going to put 3 into that top thing. But not really. I'm going to put 2.999999999 in. But it's going to act like 3. So here's what I'm going to do. This is the middle part. 3 minus 1 is 2. 2 squared is 4. Right? 3 minus 4. So this is going to be 2 minus 3, which is -1. So f at 2.999 is close to -1. So guess where this graph does? I have an open circle down here at -1. What we will do tomorrow, and I have this assignment right here, and what we will do tomorrow